在相爱相杀中，分别开拓广义相对论和量子力学。1936年，图灵在研究可计算数的过程中，开始图灵通用机的探索。1945年，参与了曼哈顿计划的冯诺依曼带来计算机领域的三定律。1948年，香农在和冯诺依曼的讨论后提出信息熵和相蒙定理。20世纪初期，菲尔兹在证明黎曼罗赫定理的同时，致力于全球数学交流。1941年，海蒂拉玛和安泰尔发明的调频技术落地于无线通信系统。1965年，戈登摩尔总结实践经验，提出了一直被追赶的摩尔定律。2000年，高锟推动建成世界上第一条1公里长的光纤网络。1986年，杰弗里·辛顿将反向传播技术应用于深度学习。科学研究和技术发展就是这样一步步向前迈进。链接实践和整合资源，积极探索和开拓创新，讨论碰撞和相互激发，人才发展和融合生态。查斯乌科技网站汇聚全球高价值科技和学术信息，提供多种模式智能高效服务，链接全球学术、技术和人才资源，链接、创新、激发、融合。查斯乌科技网站与你携手并肩，共同促进全球科学和技术的进步。科学和技术的进步源自于什么？是在实践中的启示，是在探索中的火花，是在碰撞中的激发，是在融合中的升华。1654年，帕斯卡和费马在分补助问题的讨论中，开启概率论的大门。1687年，牛顿在哈雷的鼓励下，积极研究并最终出版《自然哲学的数学原理》。1736年，欧拉走过哥尼斯堡7桥，并开创图论这门新的学科。20世纪初期，爱因斯坦和波尔在相爱相杀中，分别开拓广义相对论和量子力学。1936年，图灵在研究可计算数的过程中，开始图灵通用机的探索。1945年，参与了曼哈顿计划的冯诺依曼带来计算机领域的三定律。1948年，香农在和冯诺依曼的讨论后提出信息熵和相蒙定理。20世纪初期，菲尔兹在证明黎曼罗赫定理的同时，致力于全球数学。
Good afternoon, everyone. It's a great pleasure to be here again for this online seminar hosted by Park and OTF ISAC. And today, we are very honored to have our old friend from Park, Professor Fan Liu from Southeast University, giving a talk on the topic of which communication waveform is optimal for sensing. Professor Liu is actually an old friend of us, and he is currently a professor with the National Mobile Communications Research Laboratory, School of Information Science and Engineering, Southeast University, Nanjing, China. Prior to that, he was an assistant professor with the Southern University of Science and Technology, Shenzhen, China, from 2020 to 2024. He received his PhD and bachelor degrees from Beijing Institute of Technology in 2018 and 2013, respectively. He has previously held academic positions in the UCL as a visiting scholar from 2016 to 2018 and a Marie Curie Research Fellow from 2018 to 2020. Professor Liu's research interests lie in the general area of signal processing and wireless communications, and in particular in the area of integrated sensing and communication, ISAC. He is the founding academic chair of IEEE ComSoc ISAC Emerging Technology Initiative, vice chair and founding member of the IEEE SPS ISAC TWG, an elected member of IEEE SPS Senior Array and Multi-Channel Technology Committee. As an associate editor of IEEE TCOM, TMC, and Open Journal of Signal Processing. And he is also a guest editor of IEEE JSAC, Wireless Communications, Vehicular Technology Magazine, and the moderator of the archive EESS area. There are too many good things of fun, and therefore I don't think I have the time to explain everything here. But he has also received several prestigious awards and holds and is very active in the topic of in general in wireless communications. And noticeably, he has received the 2025 IEEE Communication Society and Information Theory Society Joint Paper Award, 2024 IEEE Signal Processing Society Best Paper Award, and also 2023 IEEE Communication Society Stephen O. Race Prize. And without further ado, please join me to welcome Fan for today's talk. Thank you.
Okay, thanks for the very nice introduction. And I assume that all of you can see my screen now.
Yes, it's very good.
Okay, so it's been a great pleasure and honor to come back again as a speaker. So last time I was here as a host, actually. So today I'm going to introduce our very recent progress on the optimal waveform design for ISAC. So today my talk has a very simple title: which communication waveform is optimal for sensing? Okay. So let me first introduce the background and motivation. So I'm not, I think all of the audiences, most of the audiences should be very familiar with the concept of ISAC. So I'm not going to spend too much time here. So I just wish to emphasize that recently ISAC was recognized by both the ITU and 3GPP as one of the 6 key usage scenarios and the 9 research objectives for 6G. So these 9 research objectives was recently, I think that it was back to last year, June, that has been recognized by 3GPP, okay? So as we can see that ISAC has been a very important topic in 6G and a very new feature for our future wireless communication systems. Okay, so if we look at the 5G advanced based ISAC, we could see that there's basic sensing functionality which has already implemented in the 5G advanced system. So basically in the 3GPP protocol, there is a 10% ratio reserved dedicated for sensing resources. So within this 10% ratio of resources, you may employ, let's see, physical layer reference signals for sensing, or you could employ dedicated channel chirp signals for sensing. So this kind of protocol is very easy to implement, but has a very poor performance because it only occupies only 10 to 15% of time frequency resources and results in very low sensing resolution and very low sensing accuracy. So most of the resources, more than 85% of the resources was occupied by the data payload, which carries important information. And if we wish to improve the sensing performance, we have to fully exploit this data payload signal and to see how we can use that to best achieve the sensing performance while causing minimum performance loss to communication. Okay. However, if we look at the data payloads, we could see that it is a random signal, because from the information theory we know that if a signal wish to carry some information, then it must be random. Okay, so deterministic signal has zero entropy, so it has no information. But if we look back to the radar signal processing, we see that radar systems, they typically adopt well-designed deterministic signals for target sensing, like M sequences, like gold sequences, like chirp signals. These signals are with very good ambiguity properties. But if we wish to convey information, communication data signals have to be random, like Gaussian distributed, or we employ QAM and PSK code books, which are currently widely used in the modern communication systems. However, sensing with random signals leads to performance degradation, and we have rigorously proved that in this award-winning paper. So as I just mentioned, if we look at the waveform design problem, and we have actually three types of design philosophies, but we would more prefer the communication-centric design, because for sensing-centric design, it is not compatible with the current cellular networks. But with communication-centric design, we could be fully compatible with the cellular networks. So that is why we look at this kind of communication standardized frame structure for sensing. And also we have joint design, but this kind of design always has very high design complexity, and which cannot be used in practical scenarios. So we focus on communication-centric design, but as I just mentioned, the sensing performance will be degraded due to the random data payload. Then there's a natural question. So if we use communication-centric design waveform, then which communication waveform has the optimal sensing performance? So that is the main focus of today's talk. So let's first revisit some previous findings of our group. So in this paper of the last year, we have found that CP-OFDM achieves the lowest average ranging setup level on the QAM and PSK constellations. So you could look at this figure of the average setup level of three waveforms. We have single carrier, we have CDMA, we have OFDM. And you can see that OFDM indeed achieves the lowest setup level at every delay index. Okay, and if we look at the actual ranging performance, we could see that OFDM also has the best ranging IMSE compared to the other two waveforms. So the information, the takeaway information is that there's no need to design new communication-centric ISAC waveform for ranging, okay? Because we already, reviewed that the OFDM waveform is optimal for ranging. But how about the joint delay Doppler estimation? There are many researchers, so when I was giving talks about this paper, many audiences will ask, how about the Doppler side? So you only look at the delay estimation performance. So how about Doppler? So then we would like to investigate the full delay Doppler performance. Okay. So before that, let's first introduce the basic system model that we would like to use. So here, first of all, we can see the random IID symbol. So IID means, as we know, that independently identically distributed. Okay, so have IID random symbols drawn from constellation S, and we assume that this S has some very generic mirrored assumptions, mirrored conditions on this constellation. So it has the unit of variance. So this is to control the average power of the constellation such that all the constellation can be compiled under the same average power. And the zero mean, so that means the constellation is somewhat centrally symmetric. And also we have its pseudo variance equal to 0. So that is to govern the rotational symmetry of the constellation, which means that for a constellation, if I rotate that constellation by that C 90 degree, then it is invariant. For example, PSK and any squared quantum constellation satisfy this condition. So it has 0 pseudo variance. Okay. And in the meantime, we are very interested in this particular value of the constellation, so the kurtosis. Under the above conditions, the kurtosis reduces to the fourth order moment of the constellation, which means the fourth power of the amplitude of the constellation, okay? And we take expectation over that. So if we look at common constellations, we could see that PSK has a kurtosis of 1, and all the common constellation has a kurtosis between 1 and 2, and more precisely, it's basically between 1.3 and 1.4, okay, as you can see here. And very interestingly, if we look at standard Gaussian distribution, it has a kurtosis of exactly 2, okay? And so that with that, we could very naturally divide all the constellations into 2 categories. One is sub-Gaussian, so which has a kurtosis less than 2. And as you can see, all these constellations in the table are sub-Gaussian. And super-Gaussian constellations, so with a kurtosis larger than 2. So examples include index modulation or APSK with drastically varying amplitudes. Okay, so this kind of constellation are not very commonly used, and we may use this kind of APSK constellation in let's see energy efficient scenarios. Okay, so these are some assumptions on the constellation, and then we look at our signal model, and we first look at the one-dimensional signaling. So with one-dimensional signaling, we have a so-called waveform matrix, which is U. So U here is a unitary matrix. It multiplies to the the constellation symbol S. Okay, so in that case, every constellation symbol is carried by a so-called waveform, or more precisely, a waveform basis. Okay, so as you can see, these waveform bases, they are orthogonal to each other, and some typical examples are here. So if we consider single carrier, then U is an identity matrix. Then these waveform bases are nothing but delta functions. Okay, so they are orthogonal to each other. And OFDM, then U is an IDFT matrix. And in this case, these waveform bases, they are nothing but cosine signals. And the OTFS, which is written like this, we have IDFT canonical with identity matrix. And in such a case, the symbols are placed in the delayed Doppler domain. Okay, and in the first 2 cases, the symbols are placed in the time and frequency domains, respectively. And AFDM. So AFDM are composed by the so-called chirp basis. And as you can see, we have an IDFT matrix here, and we have 2 diagonal matrices represent the faces, the quadratic faces of the chirp signals. And these matrices actually consist of n orthogonal chirp signals. Okay, So all these waveform bases, they're unitary metrics, and we use this UN represent the unitary group of size n. Okay, then let's look at the two-dimensional signaling, which might be more practical in our current communication signal system. So if we arrange all the constellation symbols into a matrix of size n by m, so we have a matrix S here, as you can see, and then we could have two waveform bases instead of just one. Okay, so applied to the columns and rows of S. Okay, then in that case, this U is a unitary matrix, and this V is also a unitary matrix, and the signal matrix X, its columns are named as the so-called slow time. Okay, and if you think about OFDM, this one slow time index is actually a OFDM symbol, and each of the rows is named as a fast time sample. And again, if you think about OFDM, then each row is a subcarrier. Okay, so we have fast time, we have slow time, and typically we use fast time to measure the delay of the targets, and we use slow time to measure the Doppler of the targets. Okay, so but this subject to some assumptions, and this kind of assumption only hold for, let's see, low mobility scenarios, and I will introduce that later. And in practical systems, we will never be able to, really transmit a matrix. We will have to use a serial parallel to serial transmission, which mathematically is to vectorize this X. Okay, then you can see that our signal becomes like this. So we have V transpose connect product with U multiplied to vec S. Okay, and then this X1, X2, Xm, they are transmitted in a serial manner. Okay, so there are typical examples. So if we take U and V both as identity matrices, then you can see that this is again single carrier. And OFDM, then I just need to make this V matrix simply identity matrix. And OTFS is just the opposite. U is identity matrix and V is the IDFT matrix. So AFDM, again, we could use this so-called IDAFT matrix as U and use identity matrix as V. Okay, so with that, we could have a two-dimensional signaling, and in practical system, all the signals in the time domain, they're actually firstly arranged into this two-dimensional signaling and then transmitted in a serial manner. Okay, so this is a two-dimensional model, and then I would like to introduce our main role of today's talk, the ambiguity function. Okay, so this is a very important sensing performance metric. So if we look at a continuous time signal, let's see xt, then the ambiguity function, which is a function of delay and Doppler, is defined in this way. We have xt multiplied to xt minus tau conjugation, and then multiplied to a Doppler phase term, ej 2 pi nu t, and then we take the integration over t. Okay, then we have an ambiguity function, and in the radar signal processing, it is well known that the saddle level of the ambiguity function measures the multi-target interference. So it is also worth mentioning that in a recent 3GPP Round 1 meeting, which was held last month in Dalian, China, they have an agreement that they will use AF, so ambiguity function, as a performance metric to measure the sensing performance of ISAC waveform. Okay, so this agreement has been reached last month. So as you can see, ambiguity function is by default a facial sensing performance metric for ISAC waveform. But in our case, we would like to consider here the discrete case. So here we have a continuous time signal, continuous ambiguity function, but for mathematically for mathematical simplicity, we would like to use discrete modeling. So here, to have discrete modeling, we have to first understand how to model time shift and the frequency shift by discrete matrices. So here, we could first have an aperiodic time shift matrix, which is J tilde nk. So this is a size n matrix, which will delay the signal by k samples. So if you multiply this J tilde matrix to a size n signal, you will simply delay that signal by k, okay? And then frequency shift matrix, which is a diagonal matrix. If you multiply that diagonal matrix with the signal, you will see that you actually have a phase rotation on each of the signal sample, right? And this phase rotation is actually linear in time, so it can be modeled as a column of the DFT matrix. Actually, it's IDFT matrix here, okay? So which is written in this way. And in practical system, we have also a cyclic prefix appended to the signal. So if I append a CP to that signal, we have an ACP matrix. And at a receiver, we would also like to remove that CP, and which can be mathematically represented as a RCP matrix in this way. And there's a very interesting property, which is that if you multiply this J tilde matrix, which is aperiodic time shift, by RCP and by ACP, you will get a periodic time shift matrix. Okay, so in that case, the delay is repetition of your. So with this matrix and with this frequency shift matrix, we would like to introduce another very fundamental, very important mathematical tool to characterize the property of ambiguity function, which is the Weyl-Heisenberg group. So the definition of the WH group is basically like this. So GKQ matrix is simply the product of the Q Doppler matrix and the kth delay matrix. So here we use periodic delay, okay? And then if you multiply that GKQ with a certain phase EJL 2 pi over n, and then this LKQ are taken from, for example, all taken from 0 to n minus 1, then you get basically, the cubic n, matrices, okay? And these cubic n matrices will form a set. So this set is called Weyl-Heisenberg group, okay? So this is a group. So from the group theory, we know that every group will have certain features like a closure, which means that if you take two elements from this set, and if you calculate their product, the product is also an element in that set. So that means this set is closed. And associativity, which is obviously because the matrix product, matrix multiplication itself has associativity property. And then it should have identity and inverse element. Identity is simple. We just use identity matrix as an identity element. And the inverse element means that every GKQ will have another matrix. If you inverse GKQ, if you multiply these two matrices, you will get identity matrix. And that is also obvious because you could always have, for example, delayed by k and then delayed by minus k. And then if you have a Doppler phase of q and then another Doppler phase of minus q, they are all in this site, right? So they have this. So if you have a GKQ, you must have inverse of GKQ, okay? So what is interesting about this WH group is that it is a non-commutative group. So what does that mean? That means that if you look at two elements in this group, GMN and GPQ, you can consider its product. then you could see they are not commuted to each other, right? So GMN multiplied to GPQ does not equal to GPQ multiplied to GMN. They have a different phases, okay? So why is that? The basic principle roots fundamentally in the non-commutation relation between time and frequency shifts. So that means if for a signal, if you first perform time shift and then Doppler shift, or you first perform Doppler shift and then time shift, you will get two different signals. They will have a phase term. So this phase term is known as the so-called twisted convolution. Okay, so basically the time and frequency shifts, they are not commutative with each other, and this is nothing but Heisenberg uncertainty principle in the quantum physics. Okay, but so it applies to any Fourier pair. So time and frequency, time and time and energy, and all this Fourier dual, they will have the so-called this uncertainty non-commutative relationship. Okay, so that is some basic properties of Weyl-Heisenberg group. And then we would like to look at the mobility. So mobility is very important because our modern communication system, they will be designed with respect to different degrees of mobility. So for high mobility and for low mobility, the design methodology, the design philosophy can be very different. So let's look at the mobility from the two-dimensional signaling model. So we have slow time, we have fast time, and if we have high mobility, then if we look at a slow time sample, then you could see that the Doppler phase within this sample is faster varying at each fast time sample, right? So I use different colors to represent the Doppler phase. So that in the modern OFDM system, you will always cause the so-called intercarrier interference due to the fast varying Doppler phases. Okay, and so this is high mobility case. And if you look at the low mobility, which is most of the case in our daily life, you could have a very elegant approximation that within each of the slow time sample, the Doppler phase varies slowly, such that all samples, all the faster time sample within the same slow time block can be seen as approximately sharp and identical Doppler phase. So you can see that their color are the same, right? So these are two different modeling, considering the fast varying or slowly varying Doppler phases. Okay, and they will be very different if we consider ambiguity function under these two different mobility scenarios. Okay, so let's first add the high mobility sensing metric, which is which we call discrete periodic ambiguity function. It is actually the classical ambiguity function, but which has been discretized and has a CP, so it has a periodicity here. So we have DPAF as a high mobility sensing metric. And here, this is a signal processing pipeline, and we have our random beta stream mapped to some constellation symbols, and then modulates on some waveforms. And then we append some CP on that signal. And then when the signal is received at the receiver, the CP will be removed. Okay, then we get this RCP X tilde. So if we have multiple targets, we'll end up with this signal. Okay, so as you can see, we have each target, the Lth target has a delay KL, Doppler QL, and amplitude beta L. And so this is Doppler, this is delay. As you can see, this kind of model is also known as doubly selective channel in the wireless communication system. But here in radar signal processing, we do not have such concept. we just use this signal to represent the multi-target reception with both delay and Doppler. Okay. So this is, with that, we have this Y, which is our observation, right? And for sensing signal processing, we usually use matched filtering. We multiply this Y with a delay, with a time and a frequency shifted version of X. So we could get this, okay? And as you can see, this is nothing but a linear combination of time shifted and frequency shifted version of this discrete periodic ambiguity function, which is defined like this. And it is a linear combination because we have this amplitude term here, and also, of course, plus a noise, okay? So with that, as you can see, if you have multiple targets, then they will have interference with each other. And this interference is usually characterized by the saddle level of the ambiguity function. So that is why ambiguity function is very important in radar signal processing. And here, because the ambiguity function is a complex function, to measure its saddle level, we use the square of that ambiguity function. And more importantly, because we have random data signals in X, right? So we will need to take an expectation of that saddle level, which we call ESL, expectation of the saddle level. And the summation of all the saddle levels is the so-called EISL, so expectation of the integrated saddle level, okay? So these are the metrics that we would use in measuring the DPAF. And then if we look at the low mobility sensing scenario, then we use another ambiguity function called the faster slow time ambiguity function, FST-AF. So this ambiguity function is actually an approximation of this guy, of this DPAF. So the whole process is the same, but all the signal processing is applied to each of the column one by one, okay? And then with that, we would end up with something like this, okay? So as you can see, this is approximation. And the multiplication of Doppler and the delay matrix, they has been replaced by the Kronecker product. So Kronecker product usually means that the two terms are decoupled with each other. As you can see, that is indeed the truth. So with this observation, this is not a doubly selective channel anymore. And I think in the wireless communication, this may be termed as quasi-static channel because the Doppler phases is assumed to be constant over each slow time index, okay? And with the matched filtering, we use this, version of the time and frequency shifted signal of X to do the matched filtering. Then we end up with this. And then the FST-AF reads like this. So as you can see, we just replace the matrix multiplication here by the Kronecker product, right? And an alternative expression of the FST-AF is like this. So we calculate the frequency slow time domain, matrix of the signal. So X here, this guy is defined over the time domain. And if you take the Fourier transform to its columns, then you will get a frequency time domain, which is like this. And you can compute the element-wise square of this XFT. And then we take the two-dimensional DFT at the columns and the rows, right? Then you get the FST-AF. So this expression has a very interesting interpretation, which is that the frequency slow time domain has a dual domain, which is the delay Doppler domain, okay? So if you take the two-dimensional DFT to the signal in the frequency slow time domain, you will get the signal in the delay Doppler domain. So I think that is also a very basic principle in OTFS. So again, we need to measure the ESL and EISL in that case, which can be written in this way. Okay, so that's all for the metrics and models, and then we will have to introduce the mean results. So do we even have a optimal waveform if we measure the sensing performance using these ambiguity functions? So let's first investigate the DPAF, which is a matrix in the high mobility scenario. So there's a very trivial proposition, which is that if we wish to have a waveform to minimize the EISL in DPAF, no such waveform exists. Okay, so for all constellation and the modulation scheme, the normalized EISL, so we have to normalize it with the mean lobe level here, is equal to a constant number n-1. It has nothing to do with the waveform and nothing to do with the constellation. Okay, so no optimal exists in terms of minimizing the summation of all the ESL. So that is a very trivial property, because if you look at any radar textbook, maybe the second chapter will introduce ambiguity function, and there's a very important property of the classical ambiguity function, which is that its volume is invariant. So any ambiguity function has an invariant volume. So the volume is actually can be measured by the ISL here. Okay, so that is just textbook knowledge. We are more interested in, so can we have some locally optimal waveform and minimize not all the saddle level, but part of the saddle level. So that is also very useful. But I will show you next that this kind of waveform does not exist either. So here, we could first look at the closed form expression of the average squared discrete periodic AF, which is written in this way, as you can see here. Okay, so you can see that the waveform matrix affect this ambiguity function through this term. And it has different signs depending on this kurtosis. So if for sub-Gaussian constellation, this kurtosis -2 has a negative sign, then if we wish to minimize the saddle level, we need to maximize that this summation. On the other hand, if we wish to have super-Gaussian constellation, then this is a positive sign. Then to minimize the saddle level is to minimize this summation. Okay. So I will show you that if we wish to minimize the saddle level for the sub-Gaussian case, okay, the lower bound for the ESL is achieved if and only if this DNQ-JNK matrix is diagonalizable by U. Okay, so that means we will have a U matrix multiplied to its Hermitian to the left side and the self to the right side. Then we have a diagonal matrix. So the necessary and sufficient condition to attain the minimum ESL is that this matrix has to be diagonalizable by U. Okay, so this is a very strong condition. And we could have some examples here. So the matrix is set. So if we let this k equals to 0, or we let this q equals to 0, we get the pure Doppler matrices or the pure delay matrices. They are respectively diagonalized by identity matrix and by IDFT matrix, right? Because for this guy, this D matrix is already a diagonal matrix. So it is definitely diagonalized by identity matrix. And for this guy, so when q equals to 0, this D is identity matrix. And this J is a circulant matrix, as we all know. So any circulant matrix can be diagonalized by IDFT matrix. Okay, so this implies that the single carrier and OFDM waveform respectively achieve the minimum ESL at the 0 Doppler and the 0 delay cards of the DPAF. So this is consistent with our previous findings that OFDM waveform achieves the lowest average setup level for the delay set loss. Okay. So if we look at this proposition 1, we know that no optimal waveform exists to minimize the summation of all the ESL. Then we ask a second question. Can we design a waveform that minimizes the setup level with the prescribed two-dimensional delay Doppler region? We know that we have such waveform for one-dimensional case, right? For the zero Doppler cut or the zero delay cut, we have single carrier and OFDM to minimize the setup loss. But can we find such kind of waveform that minimize the setup level within a two-dimensional region of the delay Doppler region? And this two-dimensional region should be continuous, right? So if such waveform exists, then we will be also very happy, because with that we could have this waveform operate in some targets and with such delay and Doppler that within this region, this waveform is optimal. So can we have such waveform? And unfortunately, our investigation, our results showed that even this kind of waveform does not exist. Okay, so how can we prove that? We use a group theoretical argument. So remember that we have mentioned that these delay and Doppler matrices, they are elements in the Weyl-Heisenberg group. And with the property of the group, we could first prove this theorem, which means that if we have some delay Doppler matrices that can be diagonalized by some waveform, okay, and then we take this index into a site which is called IU. So this GU is the site of all diagonalizable GKQ, and this IU is its index site. Then we could see that for any AB within this index site, it is impossible that AB plus 1, A plus 1B also belong to this index site. Okay, so what does that mean? This sounds a little bit odd, but if you think about it carefully, this theorem actually means that there's no such waveform that can minimize the setup level over a 2x2 region, okay? Because you can say AB plus 1, A plus 1B, and also A plus 1, B plus 1, they will form a continuous 2x2 region in a delay Doppler domain, right? If these points, they cannot coexist in this index site, that means that these four delay Doppler matrices, they are not, it is not possible for them to be, simultaneously diagonalized by this U matrix, right? So if you cannot form a 2x2 region, you cannot form a even larger region, right? So that means it is impossible for any waveform to generate a valid low ambiguity zone pattern that achieves the minimum ESL in any specified two-dimensional compact region over the delay Doppler domain. So that is unfortunate news, right? We cannot have this kind of waveform. And even worse, we could prove that given the orthogonal modulation basis, this kind of diagonalizable matrices, only the number of this kind of matrices is no larger than n. But we have n square, right? We have n square matrices in the whole delay Doppler region, but there are only n matrices can be simultaneously diagonalized by a single U, right? So that is very unfortunate. And moreover, any 3 points in this index site are either collinear will form a triangle with an area no less than n over 2. So that means all this minimum cellulose must either lie on a single line or be highly dispersed, in the sense that any 3 non-collinear points enclose an area of at least n over 2. Okay. So these are all mathematical results. If we look at the numerical results, you would figure out what I'm saying here. So if we look at these ambiguity functions, all these delay Doppler beams, they are represented by a delay Doppler matrix, and it has an index, right? A delay K and Doppler Q. And the diagonalizable matrices, they will form this very low saddle lobes on the ambiguity function. So apparently, if we look at OFDM, all these low saddle lobes are placed in the time domain, sorry, in the delay domain, right? Purely in the zero Doppler card. And if we look at single carrier, all these minimum saddle lobes, they are placed in the Doppler domain, so they are placed in the zero delay card, right? So this is consistent with these two examples we have just mentioned. And if we look at OTFS, these lowest saddle lobe levels, they were placed in a grid by of N1 by N2 grid, okay? It's like this. And if we look at the AFDM, it will be all these lowest saddle levels will be placed on actually a line, modulo N line. It's a modulo N line, right? So it's a line from here and then go back, and then another line and then go back again, okay? So this is also determined by the property of AFDM. So as you can see, our results are very clear that these lowest saddle levels, they can any form a line modulo N, so either a straight line or a line like this, or it has to be highly dispersed such that any of these three saddle lobes, low saddle lobes, will form a triangle of an area larger than N over 2. Okay, so they're highly dispersed. That means they cannot be concentrated in a compact two-dimensional region. Okay, so that is determined by the algebra architecture of the WH group. Okay, so in that case, we cannot find even a locally optimal waveform in the case of discrete periodic ambiguity function. So that's very unfortunate. So here are some case studies. We have explicitly derived the average squared dPAF of different waveforms, OFDM, single carrier, and OTFS, and also AFDM. And as you can see, the AFDM case, these lowest saddle lobes, they will be placed in this line modulo N. Okay, so this is a line with actually with a slope of up to NC1. Okay, and with OTFS, all the lowest saddle lobes are placed over an N1 by N2 uniform grid. Okay, which is determined by this. So with that, we have some conclusion about the classical ambiguity function, and here we name it as dPAF. So how about the fast slow time ambiguity function? We have some good news here. So if we have small Doppler, we have quasi-static channels, then our ambiguity function can be approximated by this fast slow time ambiguity function. So which has a EISL written like this. Because this is not a classical ambiguity function, so the volume invariance does not hold. So actually, if you look at this term, if we wish to minimize the EISL, it also depends on the sign of this kurtosis -2, right? So if it's sub-Gaussian, then we have to maximize this guy. If it is super Gaussian, we have to minimize this guy. So that will give us two different, solutions. So to maximize this guy, we need V to be identity matrix, U to be IDFT matrix, such that in this alpha norm, we will have an identity matrix. So that will maximize this alpha norm, and this will result in OFDM waveform. So for super Gaussian constellation, if we minimize this guy, then we will have V equals to IDFT matrix, U equals to identity matrix, which will give us a constant modulus matrix, and that will give you OTFS. Okay, so with that, we could prove that OFDM and OTFS achieve the lowest EISL FST under sub-Gaussian and super Gaussian constellation, respectively. And there are some even better news. That is that so OFDM and OTFS are not only two optimal waveforms that minimize the EISL, they also minimize every setup level at the every delay Doppler bin. So EISL minimization problem can be written in this way. So again, if it is sub-Gaussian, then this is maximized. If it is super Gaussian, then this is minimized. And then OFDM and OTFS achieve the lowest ESL at each delay Doppler bin over the fast slow time ambiguity function for sub and super Gaussian constellation, respectively. And again, we derive the closed forms for STAF for single carrier, for OFDM and for OTFS, and also for AFDM. Okay, so as we can see, the numerical results is like this. So in these numerical results, we could see that for fast slow time ambiguity function, OFDM and OTFS, they have lowest saddle level for sub-Gaussian and super Gaussian, respectively. And for super Gaussian, sub Gaussian, they are the worst. Okay, so in the opposite way. So you can see each saddle level they are minimized, and they are basically this. We have a very flat average saddle level over the whole delay Doppler domain for both OFDM and OTFS. And for single carrier, again, the Doppler it only minimizes the zero delay cut. And for EFDM, the thing becomes a little bit different, as you can see that there are some minimum saddle level over these lines. Okay, and this is again determined by the structure of AFDM. Okay, so I think that's all the main results, all the technical results that I wish like to present. And here are some takeaways. So the main contribution of our work is that we have developed a unified framework to characterize the ambiguity properties of random communication waveforms, and more precisely for any linear unitary communication waveforms. Okay, and we derived the closed form expressions for ESL and EISL on both ambiguity functions. We revealed how modulation waveforms and the constellation statistical properties affect ambiguity functions. And two design insights. For high mobility scenarios, no orthogonal waveform can achieve the minimum ESL over any compact two-dimensional delay Doppler region of the DPAF. Hence, there's no optimal communication waveform under the DPAF framework, even in a local sense. So that means that this is a no-go result, right? So that means that if you are still investigate optimal ISAC waveform in high mobility scenarios, I will see that that is a dead end. There's no need for that kind of research because there's no optimal waveform in that case. But for low mobility scenarios, as we have just said, the OFDM and the OTFS, they are two optimal waveforms for sub-Gaussian and super Gaussian constellation, respectively. Okay, so that's all for my talk. And if you are interested in the technical details, you can look at this paper that we have uploaded to the archive. Okay, so thanks for listening, and I'm open for any questions.
Thank you, Fan, for the great talk. It's very informative and theoretical. We do receive several questions regarding your presentation, and to be honest, I think most of them are just like for you to clarify on some of the key ideas in this talk. So I will rephrase a little bit to make it more aligned with your theme. So I think the most of the work we discussed today is actually focusing on the ambiguity function. Would you like to elaborate on how this is connected to a more general sensing metrics such as CRB, zigzag-high, and how ambiguity function can reflect the actual sensing performance?
Okay, so that is actually a very good question. So ambiguity function actually has a very deep connection to this fundamental estimation theoretical bounds, like you just have mentioned CRB and ZZB. So for CRB, we have a recent paper here, the reference 2, as you can see here. So if you're actually very interested, you could look at the details. And we have discussed some connections between ambiguity function and CRB in that paper. So very basically, if you look at CRB, you know that it is the inverse of the facial information matrix.
Right.
And for the facial information matrix of delay and Doppler, its elements is actually determined by the ambiguity function. So the min log of the ambiguity function actually contributes solely to the diagonal elements of the facial information matrix, and the side lobes will contribute to the off-diagonal elements. So that is why we need very high min log and a very low side lob. That will give us more positive semi-definite positive definite facial information matrix.
Right.
And it will give you smaller CRB if you take the inverse of that facial information matrix. Okay, so that is a very deep connection between ambiguity function and CRB. And for ZZB, there's also a very clear conclusion in a single target case. So in a single target case, the ZZB is a nonlinear function of ambiguity function.
Mm-hmm.
Okay, so ambiguity function actually determines very fundamentally how these bounds behave at the C.
Right. Okay, thank you. And another half of this question, how ambiguity function, good ambiguity function reflects actual sensing performance?
Like I just said, I think I have already answered this question. So if you have low side lobes and high main lobe, you will get very good facial information, and then that will give you smaller CRB.
Okay. Another question from the audience is about the kurtosis. You have mentioned that for most practical communication constellations, the kurtoses are smaller than 2. Do you have any insights why they're always smaller than 2?
Okay, so that is also a very interesting question. So again, let me first highlight that for the kurtosis of 2 is exactly the value for Gaussian constellation. And so for other sub-Gaussian constellation like Quam and PSK, that means that basically if you look at the PDF or look at the distribution, and you will see that its variance, we would see that the high amplitude parts would have lower probabilities. Mm-hmm. Okay, so that means its amplitude may be more concentrated in within some region if you compare it with Gaussian. So that is very natural for the modern communication systems. So if you have a super Gaussian constellation, that means you have a drastically varying amplitudes in your constellation symbols, and that will cause very high fluctuation in the transmission power and will cause problems like a PAPR in the OFDM sense, and which also give you a very high requirement for the power amplifiers. So most of the modern constellation symbols, their amplitudes may not spread very widely. Okay, so that is the insight.
Right. I have a follow-up question on this, on what you have mentioned. What about the pre-coded communication signals, or say general channel coded systems, where there's a not unitary transform? It's something not unitary, and well, how about that affect the ambiguity function?
That's a very good question here. So if you look at channel coded signal, that will sometimes, so I'm not an expert for channel coding, but for channel codes, we know that will introduce some correlation between the symbols. Let's see, and then the symbols are not IID anymore, and then our whole derivation might be changed, and we cannot use this kind of framework. So if you consider channel coded signals, then I would see we'll have to look at the basic mechanism of how channel codes affect the ambiguity properties of the signals. I think that's a very interesting topic that's worth further investigation. And for pre-coding, I think it is actually has have a simpler structure, because if you look at precoded symbols, then it is just a mix of symbols, and that will give you again not IID, but it will change its kurtosis. Let's see. For sub-Gaussian, it will increase its kurtosis. For super Gaussian, it will reduce its kurtosis. So that will give you some influence on the constellation symbols.
Right. In my opinion, I think it is possible to further extend what you have mentioned to pre-coded case, because you can always insert your pre-coding metrics into the, so for example, Wheeler-Heisenberg group, and then discuss its properties.
Yes.
Right. Okay. Another question is about the fast slow time ambiguity function you have mentioned. The audience are asking why this is suitable for low mobility sensing scenarios.
Okay, so like I just mentioned here, if we look at the low mobility scenario, we could reasonably assume that the Doppler phases remains approximately constant at a slow time block like this. So you can see that all these colors are the same, right? And with that, the coupling between Doppler and the delay matrix, in the previous case, you have multiplication between them, so there are some coupling between them. They will be decoupled in the low mobility scenarios. That means this delay Doppler matrix will be written in this way as a Kronecker product. So with Kronecker product, that means the Doppler phases, the Doppler shifts only affect slow time, right? As you can see, only the slow time, the colors will change. And the delay part will only affect the fast time, like this, okay? So they will be decoupled with each other, which can be mathematically written in this way. So that is why we could model it like this.
Right. Okay, I think that's all for the audience question. I have two personal questions I would like to ask your advice. I think that this whole framework is very nice. Of course, I'm also involved in some of the discussions. I wonder, what do you think of the case where we do not have this critical sampling assumption anymore, in the sense that, for example, the frequencies spacing, subcarrier spacing, and time duration, they are no longer has the product equals to 1. For example, if we are in the oversampling case, well, the derivation also holds here.
Are you talking about faster than Nyquist or something like that?
No. I'm just talking about Wheeler-Heisenberg group. When we are having this WH group, we have this frequency spacing and time spacing equals to 1.
They're perfectly orthogonal to each other, you mean, right?
Right.
Yeah, so that is a very interesting question, and I would see that the Weyl-Heisenberg group were more basically Heisenberg group. They are only in holds in two cases. One is like this: you have this Nyquist sampling of the frequency, and you get exactly n-cubic elements, right? And the other case is fully continuous. And in these two cases, you will have a group properties of these elements. Otherwise, if you have this oversampling, then there will be no group properties. You cannot form a group. So we will need to either discuss this Nyquist sampling or the fully continuous case. So that is my opinion. Yeah.
I see. Okay. My last question is more towards practical side. When you're having this ambiguity function with different waveforms, and I mean the numerical results, I see that, for example, OTFS achieves this lowest side lobes periodically. But however, in practical, I mean, communication systems or in general sensing scenarios, we have this so-called underspread assumption, meaning that the maximum delay and maximum Doppler, their product is smaller than 1. Does that supposed to mean that for OTFS, because the period for this low side lobes is T or 1/T, so we are always suffering from this high side lobe case?
I think you're talking about the fractional delay and fractional Doppler timing.
Yeah, sort of.
Yes. Okay. So in that case, again, we will have to look at a continuous ambiguity function. This is not characterized in this framework, right? So in this framework, we only look at the Nyquist sampling points. But if you look at the fractional delays and fractional Dopplers, then that might be some points in between. Let's see, these symbol durations were subcarriers. So with that, the ambiguity function can be different, but I'm not sure how does it look like. And I think that is also a very worthwhile investigation in the future, that we need to really fully characterize the ambiguity property for the whole continuous time, continuous frequency domain. Yeah.
Okay. Thank you very much, Fan. That's a very good answers for all the questions. Okay, seems like we already have quite a lot of time for today's discussion, and I would like to thank you, Fan, again for the great presentation. And I think that is end for today's presentation. Thank you very much.
Thank you.
Thank you, and bye-bye.
Bye-bye.